This is HRW911P089. With axle and spokes of negligible mass and a thin rim, a certain bicycle wheel has a radius of a number and weighs a number. First thing I want to point out, if the axle and spokes are of negligible mass and it has a thin rim, we can treat this as a thin hoop. So the rotational inertia will be mr squared. It can turn on its axle with negligible friction. Now the man holds the wheel above his head with the axle vertical while he stands on a turntable that is free to rotate without friction. The wheel rotates clockwise as seen from above with an angular speed of blah blah blah. The rotation, and its turntables initially rest. Rotational inertia of the wheel, man, turntable about a common axis of rotation is 2.1. The man's free hand suddenly stops the rotation of the wheel relative to the turntable. Determine the resulting angular speed and direction of the rotation system. Okay, so we've got this this person. Let's see. We've got this person basically holding a wheel above his head. And they're all on a turntable. So this whole thing could turn if it wants to. So right now, as seen from above, so try and think of yourself as looking up from above, this thing is turning clockwise, so it's kind of like this. Alright, so as seen from above, it's turning like this. Alrighty, now, right now, the wheel is spinning but the person's not, but the whole thing could turn on a common axis, which might be something like here. The whole thing could turn around that. Okay, that's important. And they want to know how fast will it be turning around that if he reaches up and stops the wheel. So this is a conservation of angular momentum problem. Remember that with... Oh, just a second. Sorry about that. My cats were fighting. I had to go stop them. Probably didn't hear it, but there was a loud... Anyway. Okay. Okay. Oh, what were we saying? Oh yeah, conservation momentum. If there's no outside forces, and there aren't, because all the forces are internal, he grabs this thing with his own hand and he's part of the system, then the angular momentum when we start should equal the angular momentum when we're done. So the angular momentum when we start, well, there's only one thing moving, so it's just the angular momentum of the wheel. Okay? And then when we're done, it'll be the angular momentum of the wheel, man, turntable system. Angular momentum in general is rotational inertia times rotational velocity. So the angular momentum of the wheel should be the angular momentum of the wheel times the initial rotation of the wheel, which I've put over here as omega naught. It was 57.4 radians per second. Okay. The angular momentum of the wheel, man, turntable system will be the rotational inertia of the wheel, man, turntable system times our final rotational velocity, which that is what we want right there. That's what we want. That's what we're going for. Okay, in fact, I'm just gonna solve for it now. Why not? Just divide by that. Over here, I said that this was this. I called it I total, so I'm gonna just start calling this I total. So I don't have to write all those subscripts all the time. Okay, so I end up with what I want for my answer is going to be the I of the wheel, omega naught, over the total I. Now, they gave us a number for omega naught and IT. All we need to do is put in I of the wheel, which for a wheel, any wheel, that's that thin hoop, is mr squared. Ooh, m got an extra bump for some reason. Here we go. Alright, so when I put that in, I get m of the wheel, r squared of the wheel, omega naught over I total. They gave us all of these numbers, so let's see, we've got, oh, they did give us the weight of the wheel, not the mass, I think. Let me go check. Oh, weighs 38 newtons. Righto. So, remember that mass and weight are not the same thing, right? So I wrote mass over here. But really, the mass should be the weight divided by 9.8, right? Divided by gravity to turn it back into a mass. So if I put everything back in here, I get 38 divided by 9.8 for the mass. R is 0.35. Don't forget to square it. 57.4 for the initial velocity. And altogether, the I is 2.1. All right, pop that all in your calculator. And I get 12.9833333333. So if you, let's see, I had 2 significant figures on all that. I have to round up to 13. 13 radians per second. Check that. Over here, yes, that is what is in the key. So we are done.